we'll start the technical session 4, which will have only one talk, Applications of Python 1 by Mr. Parag Bhattacharya again, and we will wind up by 4 o'clock. So welcome, and then I hope and wish you will have a fruitful day today also. So may I welcome the speaker of the first talk, Dr. Samrat, to please take on the session.
Thank you, Dr. Amar. May I ask you how much time can I speak for?
It is for 1 hour.
Okay, thank you.
Up to 11 o'clock.
Okay, thank you. Okay. So, good morning, participants and the organizers. I would basically speak on numerical techniques, or rather numerical analysis, and I'll keep my talk to a very fundamental level. I'll discuss only the basic concepts underlying the numerical techniques. And if you have any difficulty or any question, you can stop me in between. You can just unmute your mic and speak to me, or else you can also type your questions in the chat box. And after the session, of course, you are welcome to interact. So without much delay, let me start by sharing my screen. So I think my screen is visible to everyone.
Yes, it is visible.
Okay. So let me start by first understanding what a function is. So a function means something. If I say y is a function of x, that would mean that y depends on x. So if I have a particular value of x, my y value will depend on that value of x. Similarly, x is different now for the second point, y will also be different. X changes, y again changes. So y depends on x. So you can think like x is rainfall and y is the level of water. So more rainfall, more is the level of water in a river. So level of water in a river depends on rainfall. Y depends on x. Y is a function of x. So in this way we can understand. So y changes, x changes, corresponding y also changes. And if we can join the points, these are actually continuous points, by a line, so that gives the functional form of the line in xy plane. So this curve which I have drawn is actually y is equal to fx is equal to x square curve. So y is equal to x square, that is the functional form. So let us now understand, once we have understood the concept of function, let us now understand what is differentiation of a function at a particular point. I have a particular point xy, x1, and correspondingly the value is y1. Similarly, I can take another point x2 and the corresponding value will be y2. As I have already mentioned, function means the y is equal to a function of x means as x changes, corresponding y will also change. So for x1 I have a corresponding y1, for x2 I have a corresponding y2. Now differentiation, I think your mic is making a sound. Yeah, now it's okay. Thank you. Okay. Now, differentiation in simple words is nothing but change in y divided by change in x. So we can write y2 minus y1 divided by x2 minus x1. Of course, y2 will be f of x2 and y1 will be f of x1 because y is a function of x. And x2 is x1 plus a small amount, say h. So we can replace x2 by x1 plus h, then subtract x1 from there. So x1 plus h minus x1 will give me h in the denominator. And in the numerator, it is f of y2 is f of x2. So I can write f of x2 minus f of x1. x2 is again x1 plus h. So I can write f of x1 plus h minus f of x1 divided by h. So that is the meaning of differentiation. Of course, the condition is that the h should be very, very small. That means the change in x should be very, very small. Change in x is h here. Now, this is a very subjective statement. If I say very, very small, for someone, 1 is very, very small. For someone, 0.5 is very, very small. For someone, 0.1 is very, very small. For someone, 0.01 will be very, very small. So actually, we are not specific by saying that h is very, very small. For example, here it is written that if h is very, very small, this quantity change in y divided by change in x, that means f of x1 plus h minus f of x1 divided by h, is called the differentiation. The symbol sometimes it is written as f dash x1, and we know that it is written as dy dx also. Okay. Now, suppose in this case, change in x is, which is h, is equal to 6 minus 4, that is 2. So I write 2 in the denominator, and corresponding values of y are 36. Can you see the cursor moving? Is the cursor visible?
Yes, it's visible.
Okay. So this is 36 and this is 16. Because y is equal to x square, so whenever the value of x is 4, the y will be 4 squared, that is 16. And similarly, the value when the value of x is 6, the y value will be 36. 6 square is 36. So 36 minus 16. So this is 36 and this is 16. So 36 minus 16, that is 20. 20 divided by 2, the answer is 10. So I can say that, and 2 for some people, 2 may be very small. Say for example, for me, 2, I consider the number 2 is very small. So h is very small for me. So I can say that the differentiation is 10. But say for one of my colleagues, he may tell me that no, h is equal to 2 is not very small. Let us reduce it further. So maybe I can take the value of h to be equal to 1. That means x2 will be 5 and x1 will be 4. 5 minus 4 is 1. So in that case, 4 square is 16 and 5 square is 25. So 25 minus 16, that is the value of dy. 25 minus 16, which is equal to 9, divided by dx. Now change in x is 1, even smaller than 2. So the differentiation, you may think it is equal to 9. But that process will not stop. Someone may say that no, even 1 is also not very small. We should take 0.5. Then one of you may say that no, even 0.5 is not very small. Let us take 0.1 or 0.01, and the process will continue. So we have to find a way out. Mathematics has a very interesting tool called limits. And if we apply limit to this, if we apply the concept of limit to this problem, we need not say what the value of h is. We can complete the whole story by only saying h is a very small number, without actually saying whether h is equal to 2 or 1 or 0.5 or 0.1 or for that matter 0.01. We need not say anything. Let's see how. So I use the same formula. X1 plus h whole thing square minus x1 square divided by h. Why whole thing square? Because because my function is x square. So if I write f of x1 plus h, that means x1 plus h whole thing square. So that is the functional form. Minus f of x1, that means x1 square. So I write this functional forms, and after that divided by h. Divided by h was already there in the denominator, so I put this divided by h. I do not say what the value of h is. I only say that h is a small number. Whether it is 2 or 1, I am not saying anything. Next step, I have the functional form which is already written, the square of x1 plus h. I break it up as a square plus 2ab plus b square and minus x1 square. Then I cancel x1 square, and then the last but one line is twice x1h plus h square divided by h. H is a small number, it is not 0, so I can divide the numerator by h. If it is 0, I cannot divide anything by 0, that will become undefined. So I can divide if h is not 0. Since h is a small number which is not 0, I can divide. The moment I divide, it becomes twice x1 plus h. I have still not said what is the value of h. I am only saying h is a small number. And since h is a small number, I can say 2x1 plus very small number is 2x1 only. So without actually saying what h is or how much h is, I have completed my whole story. I have got the result of change in y by change in x, where change in x is very, very small, is equal to twice x1. And if I use this formula of twice x1, at x1 is equal to 4, I immediately get the result of differentiation is 2 into x1, 2 into 4 is equal to 8. So it is neither 10 nor 9, but the real value is 8. So change in y divided by change in x, when h is really very, very small, should be equal to 8. And that's what we have found from the formula twice x1, where we have not actually specified any value for h, because because the moment I specify the value of h, any one of you may say that this value of h is larger, we can always find a smaller value of h. So I have to keep on doing my calculation. Sometimes I may get 10, the way I have got when h was 2, then I may get the value to be 9, when the value to be 9 when we considered h to be equal to 1, and so on. So all these values 10, 9, these are not accurate. The accurate value is 8, which we have got from the formula twice x1. This formula, the differentiation of x square is twice x, is called analytical formula. And the way we have done here earlier, where we have actually taken some change in y divided by corresponding change in x, keeping in mind that change in x should be small, where we have taken actually these numerical values, is called numerical differentiation. Now, when we did numerical differentiation, we had to give a particular value of h. And in that process, there was some error, and the error was minimized by taking a smaller value of h, but even then it was there. But in analytical differentiation, where we actually applied the formula twice x1, which of course came from the original first principle formula, but we avoided giving the value of h, is actually the most correct formula, and that gave the correct result 8. So you may ask me, why not to use the actual correct formula twice x1, that means analytical formula, and why to use the numerical methods like taking actual values or actual numerical values of y2 and y1 and then divide by x2 minus x1. The answer is yes, we need not do numerical differentiation, because we'll always get a better result from analytical differentiation, that is from the formula. The reason we do is to understand the concept of differentiation, that differentiation is nothing but change in y by change in x, where change in x is very, very small. But it is not actually required because we always have formula for differentiation. It is not that if I have a complicated function like here, of course, we have x square, we can have x cube or x to the power 10x or x to the power 10 e to the power x, whatever function I have, I can always differentiate it. So differentiation formula are always available. We need not go for numerical differentiation. Of course, we have to know the differentiation process. That of course we know, but formula is always available. And if you forget the formula, then you can use the simple method of change in y divided by change in x. So suppose you forget the formula of differentiation of 10x, then of course you can take 10 of y2 minus 10 of x2 minus 10 of x1, that is y2 minus y1 divided by x2 minus x1. That will give you a closer result to actual differentiation of 10x. Okay. Now let us come to integration. Let us take the same functional form y is equal to x square. Before I start integration, let me tell you that unlike differentiation, integration formulas are not always available. So we have to do numerical integration. Many a times we do not have other options. Formulas are not available. If I give you a complicated functional form of a function, you will not be able to integrate it. And you will not be able to integrate it with formula. I mean, with you will not be able to analytically integrate it. But numerically, you can always integrate, and that's what I'll show you. Of course, x square can be integrated analytically also. We all know that integration of x square is x cubed by 3. So that is possible. But if it is a very difficult function, a complicated function, then it will not be, then we will not be able to integrate. And we have to know this basic concept of integration, that integration is nothing but area under the curve, and that is called integration. So if I want to do integration from a to b, this formula fx dx a to b, which is equal to, in this case, fx is x squared, so the result will be x cubed by 3, lower limit and upper limit b cubed minus a cubed by 3. And if my a and b are 2 and 5, say, my result will be 39. So in this diagram, you can see my lower limit is 2 and upper limit is 5. So this actually gives the area under the curve. Now let us approximate this area by a trapezium shown by the red lines. So just like area of a rectangle is length into breadth, area of a trapezium is average of the two heights. In this case, the heights are FA and FB. So this is like average length, you can say, divided and length into breadth, so multiplied by the breadth, that is h. So I should write the heights, the average of the heights, FA plus FB divided by 2, that is the height, multiplied by the width, which is h. So FA plus FB divided by 2 multiplied by the width or breadth h. So that is the area. So in this case, what is the area? The width is 2. Is it 2? No, width is 3. 2 to 5, the width is 3. So h is 3. 2 square is 4. FA is 4 plus FA is 4 because fx is equal to x square. So if my x is 2, x square will be 4. Similarly, when x is 5, its square is 25. So now I can write 4 plus 25 divided by 2 multiplied by 3. So the area of this trapezium will be 43.5. So you may say that this is my integration result, but see, our actual integration result was 39. And what we have got is 43.5. So that means there is an error. What can be the error? The error you can immediately see, the actual curve was under the blue line, and the trapezium which I have drawn with the red line has a difference with the blue line. The trapezium is having higher or larger area than the area under the blue line. Can you see that? There is a gap between the red line and the blue line. Red line is little above the blue line, so its area is higher, and that's why we are getting the area of the trapezium to be 43.5 and not 39, which should have been the actual result. So what we can do? One option is that we can improve the result, just like in earlier case, in case of differentiation, we improve the result by choosing smaller and smaller h. First we chose h to be equal to 2, and then we choose h to be equal to 1, and our result became better from, I forgot, but it became a little better. So now let us make this h smaller. So in other words, let us take 3 different trapezoids and add these 3 trapezoids, then it will be very close to the blue line, the blue curve. So what will be the area of the first trapezoid? The area will be f of x1, f of x2 divided by 2, that is the average height, average length, and multiplied it with the breadth, which is h. Second area will be f of x2 plus f of x3 divided by 2, again the average length for the second trapezoid, trapezium, multiply it by h, that is the breadth, and third area can also be found out. If I add this area, I should get the result of my integration, and you can see f of x1 and f of x4 are only appearing once in the beginning and at the last, but f of x2, f of x3, they are coming twice from previous expression and the next expression. So simple algebra will give you this result. Now here, of course, I have reduced h. Earlier h was 3, now h has become 1, 3 trapezoid. H is 1 for each of these trapezoids. But h is 1 is even not satisfactory. You should reduce that h also. So this, okay, let me before that calculate with this h what is the result. That means h is equal to 1, what is the result? I get 1 by 2, f of x1 is 4, because x1 is 2, 2 square is 4, plus 2 into f of x2. x2 is 3, so 3 square is 9, plus 2 into f of x3. 3 is 4, so 4 square is 16, plus f of x4. x4 is 5, and 5 square is 25. Result is 39.5. So you see, from 43.5, by reducing h, we have reached a much better value, which is 39.5. Actual value should have been 39, but we have reached quite close to that. Now, as I have said, h is equal to 1 is still higher. We have to reduce it, reduce as much as possible. Of course, in numerical method, h has to be given some value. We cannot just say h is a very small number. Just like in differentiation, in numerical differentiation, we had to give a value of h. We cannot just say that h is a small number. We can do that in analytical methods, but in numerical method, we have to give the number corresponding to h. Nevertheless, we can make h very small, and if we make h very small, that means we have to increase the number of divisions. Now there are only 3 trapezoids. We have to increase the number of trapezoids, and then the general formula is h by 2 f of x1. It starts with f of x1, then f of x2, twice f of x2 plus twice f of x3 dot 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 dot, twice f of xn minus n, the last but one x, and the final f of xn. So that is the formula. It is a general formula. This formula is called trapezoidal rule. Obviously, NH, H is the width of all the trapezoids. N into H gives you the total weight. Total weight is nothing but final value xn minus initial value. You can compare it with your example here. X4 minus x1 is nothing but 5 minus 2 is equal to 3, which is equal to n into h. N this time is 3. 3 trapezoids are there. N into h is 1, so n into 1 is 3. So 3 is equal to 5 minus 2 is equal to 3. There is of course no restriction on n. You can take any n, odd, even, any n. But there are some formula which are sometimes better than trapezoidal rule. I'll also give that formula. This is called Simpson's 1/3 rule, where the formula looks a little different. You have to, we can derive the formula, but right now I have shown one derivation, that is the trapezoidal rule. This similarly you can also find out Simpson's 1/3 rule, Simpson's 3/8 rule. I'm not going to derive this. And but one line I would mention that here there is a restriction on n. In Simpson's 1/3 rule, n should be even. In trapezoidal rule, there was no restriction on n. So that's how we will do numerical integrations. We'll use this formula, h by 2. Suppose in this case we have used already h by 2 f of x1 plus 2f of x2 plus 2f of x3 plus f of x4, and we'll get an integration result which is equal to 39.5, which is very close to our analytical integration. So the reason why we do numerical integration instead of analytical integration, because formula are not available for complicated functions. So if the formula is not available, we have to resort to this formula, this numerical technique formula, where we do not need to know the complexity of the functions. Whatever be the function, the formula remains the same. H by 2, f of x1. So once we know the function, we know the f of x1, f of x2, f of x3, f of x4. Whether the function is x square, or the function is x cube, or the function is x to the power 4, or any other function, this formula will remain same. Only in case of x square, say, now we have taken x cube, say, now we have taken x square. Instead of 4, I should write 2 cube. 4 is 2 square. If the function is x cube, I have to write just 2 cube. So that will be 8. Similarly, 3 cube, instead of 9, it will be 27. And so on. But the form of this formula will not change. But we know analytical formula changes a lot. If it is x cube instead of x square, immediately my formula will change to x to the power 4 by 4. It will not. X square integration formula is different from x cube integration formula, is different from sin x formula, is different from cos x formula. But numerical formula remains the same. So that's why whenever we do not know the formula, we'll use numerical techniques. But one cost is there, our result will not be very accurate. We'll have some deviation from the accurate value. But we can make closer and closer to the accurate value, the analytical value, by choosing smaller and smaller h. Right. Now let us come to solutions of transcendental equations. So there are complicated equations for which normal solutions are not possible. But to understand these methods of solution, we have to use a simple function. Just like in integration case, we used x square to understand the trapezoidal method, although we knew that x square integration is possible even analytically. So here also we'll choose a function whose solution can be found analytically very easily. But to understand the numerical methods of solution, it is easy for us to choose a simple function. So the function is fx is equal to 5x minus 8, and we want to find the solution for it. What do you mean by solution? Solution means the value of x for which the function becomes 0. In this case, it is very easy for you to find out. Put the function to be equal to 0. So 5x minus 8 is equal to 0. And then you just solve it. 5x minus 8 is equal to 0. So 5x is equal to 8, or x is equal to 8 by 5, which comes closer to 1.6. And you can see at 1.6, the function becomes 0. So this line, 5x minus 8 is a line where the intercept c is minus 8, y is equal to mx plus c, and the slope is m is equal to 5. And this line actually intersects the x-axis. X-axis is nothing but y is equal to 0. So it intersects x-axis, or it becomes y is equal to 0 whenever x is equal to 1.6. So 1.6 is the solution which we have just found by putting 5x minus 8 is equal to 0, or 5x is equal to 8, or x is equal to 8 by 5 is equal to 1.6. So this is the solution. So by seeing this curve, you can understand that the function which was negative for some values of x and positive for some values of x should become 0 for some values of x. I'm again repeating, if a function is positive for some values of x and negative for some values of x, that means somewhere for some values of x it should also be 0. Otherwise, how can it come from positive side to the negative side? It must cross the 0 value. That means it must have a solution somewhere between the positive and the negative values of x. And that is the principle of bisection method. So let us understand it. F of 0, that means the value of the function when x is equal to 0, we can immediately find it. Put 5 into 0 minus 8, the value is minus 8. In the graph also you can see whenever x is 0, the line is, the y value is minus 8. Of course, we may not be able to draw graphs every time. Here we can, here for your understanding, I have drawn the graph, but graph will not be available every time. And even if it is available, it is not very easy to read the graphs, especially when the divisions are very small. We cannot go into the minute details of the graph. Graph is just for us to pictorially understand the things, not to find out minor details. Because it will have a scale, we cannot go beyond that scale. Anyway, so 5 of 1, you can see it is equal to minus 3, because at 1, the value is minus 3 from the graph, and from here also, if you put x is equal to 1, 5 into minus 8 is minus 3. So as I have said, the solution will lie somewhere between the positive value and the negative value of f. Since both are negative, there is no reason for us to believe that the solution lies within two negative values. Then let us try for another value of x, f of 2. Now you see f of 2 is positive, plus 2. How? 5 into 2 minus 8, that means 10 minus 8 is 2. So that is a positive value. And from the graph also you can see it is a positive value. So at x is equal to 2, the function is positive. At x is equal to 1, the function is negative. That means somewhere within these two values of x, there is a value of x for which the function is 0. Otherwise, it cannot cross from negative side to the positive side. So somewhere it probably has got the 0 value. It has probably touched the, it must have touched the x-axis line. Okay. So the root lies between, the solution lies between 1 and 2. From the graph also it is clear that it is somewhere close to 1.5. So what should we do? Let us take another point between 1 and 2 and let us take the average of 1 and 2. Let us bisect 1 and 2, and we have got 1.5. Let us find out the value of f at 1.5. F at 1.5, if you put 5 into 1.5 minus 8, you will get minus 0.5. Now this is interesting. At 1.5, the value is negative. At 2, the value is positive. That means the root, that is the value of x for which the function is 0, must lie between 1.5 and 2. And that is what we are also seeing from the graph. Again, I am repeating, graph will not be available every time. But here, since it is available, we can compare. So you can see the value of x for which the function is 0 is actually lying between 1.5 and 2. Fine. But we are not satisfied yet. Let us find out what happens somewhere in between 1.5 and 2. That means we are bisecting 1.5 and 2. Bisecting means we are taking the midpoint of 1.5 and 2. 1.5 plus 2 divided by 2 is 1.75. So let us find out what is the value at 1.75. At 1.75, the function's value is 0.75. You can find it. 5 into 1.75 minus 8, that is the functional form. It will give you 0.75. Now, at 1.75, the value is positive. We have found. Earlier, we already found that at 1.5, the value is negative. So now I can conclude the root lies somewhere between 1.5 and 1.75. So now my range has really reduced a lot, and now I am confident that my solution lies at x is equal to 1.5 to x is equal to 1.75. And I know the actual solution is 1.6 because 5x minus 8 is equal to 0. If I put, immediately I get x is equal to 8 by 5, which is 1.6. So you can see by only doing 3 or 4 steps, we have come very closer to the result. Actual result is 1.6, which we have done analytically, and numerically when we are putting the numerical values and trying to do, I have already concluded that my result will be somewhere between 1.5 and 1.75. which is very close to 1.6. So this process, of course, if I continue, I may get even closer to 1.6. But let me stop here. You can do that. Of course, there the concept of programming comes. So maybe we'll be taught that when we do in Python programming, we need not stop after 2 points. We humans, we will get tired. After 2 steps, we'll say that, okay, fine, good enough. Our result is somewhere between 1.5 and 1.75, we'll stop there. But if it is a computer or if it is a program, it can go on doing the while loop. And yesterday you have already learned while loop. And it can ultimately give you the value after, instead of 2 steps, which you have done here, it may give the result after 100 steps. And that time you will see that your result will be very, very close to the actual result 1.6. So there the concept of programming comes. In our earlier cases also, when we wanted to divide the trapezoid, the larger trapezoid, into smaller numbers, we had to, in our case, we had to stop after making 3 trapezoids. But if it is a computer, it can make hundreds of such trapezoids, or it can make age values as small or very small, and its result will be very close to the analytical result. In integration and differentiation both, age value smaller means result is better. And computer can really make age value smaller by increasing the number of divisions and doing the calculation for a large number of trapezoids. For we humans, we have to stop at a larger number. Larger trapezoid, smaller number of trapezoids, which I have shown in the earlier case by taking only 3 trapezoids. Fine. This process of bisection method is of course possible without having the graph also. The graph was just for you to understand, so I need to draw the graph. And This function which we took 5x minus 8 was a very simple function for which analytical solution was already available 1.6. But if we have a complicated functions like 8 plus x minus 2 whole thing square minus x minus 4 whole thing cube, this function is not so easy for you to solve. You cannot tell me immediately what is the value of x for which the function becomes 0. Then this bisection method will be really helpful. You give one value of x, give another value of x. If you find that for one value of x it is positive and for the other value of x it is negative, you can conclude that within these two values the solution lies. Then you go on bisecting it and you can reach closer and closer to the correct value of x for which the function has a solution. Okay. Now let us come to Newton's disruption method. In bisection method, let us try to apply bisection method to this parabola. Set x is equal to 1. The value of the function is 4. And x is equal to 5. The value of the function is also 4. So both are positive. If we apply bisection method, we'll immediately conclude that since both are positive and not that one is negative and another is positive, the solution doesn't lie between 1 and 5. It lies somewhere else. So I'll keep on searching and I'll never find the solution. But actually the solution lies between 1 and 5. In the graph you can see the solution is x is equal to 3 for which the function has become 0. But bisection method, since it only says that solution lies when one value of fx is positive and another value of fx is negative, it will never be able to find the solution because in this graph there is no value of fx which is negative. All the values are positive. I have not drawn the negative side only. There is no negative side. All in the first quadrant. So for this type of things, we have to use Newton's disruption method. So how to find or what is the principle of Newton's disruption method? Let us find out. Let us take a value x1 and let us try to find out the slope at x1. So slope at x1 is nothing but the differentiation at x1, which is nothing but change in y divided by change in x. In this case, it is very simple. Change in x is x2 minus x1. And change in y is fx1 minus fx2. Change in x is x1 minus x2. So f of x2 is of course 0 because this is the x-axis. So f of x2 is 0. So I can only write f of x1 divided by x1 minus x2. Y value is 0 for x-axis. F of x2 is x-axis, so its y value is 0 or its value is 0. So I can just write f of x1. Now, as I have said, the slope is actually the differentiation. So I can write x2 is equal to x1 minus f of x1 divided by f dash x1. And you can see when I moved from x1 to x2, I have actually moved from somewhere 4.5 to a value around 3.5, which is much closer to the actual value 3. So I have come closer to 3. I can repeat this process. I now may take the tangent at x2 and find even closer to 3, and the process may continue and will get better and better results. So the general formula is f of x, x of n plus 1 is equal to xn minus f of xn divided by f dash xn. That is the general formula. You can put n is equal to 1 here, 2 here, 3 here, depending on the stage at which you are doing the Newton's disruption method. So in the first stage, n is equal to 1. So I had x2 is equal to x1 minus f of x1 divided by f dash x1. Now let us do an example we can understand. First, we have to or define, or first we have to understand what is the functional form of this curve. It's a parabola, I have already said, and you can see that it is equal to, parabola is y is equal to x square form. In this case, we are writing x minus 3 whole square because the solution is at x is equal to 3. So the moment x is equal to 3, y value becomes 0. So x is equal to 3 is the solution. If we write y is equal to x square, then x is equal to 0 will be the solution. And the parabola will be symmetric about y-axis. In this case, of course, it is shifted from the y-axis. If I take the differentiation of fx, it will be twice x minus 3. We can use simple formula of x square differentiation. X square differentiation is twice x. So x minus 3 whole square differentiation will be 2x minus 3. Okay. Once we have understood, once we know fx and f dash x, we will use the formula xn plus 1 is equal to xn minus f of xn divided by f dash xn, and we will get closer and closer to the actual root. So let us say my starting guess, I have to guess some value here. So let us say my starting guess is x1 is equal to 5. Of course, we know that x1 is equal to 5 is not the solution. X is equal to 3 is the solution. Here we know because we know the graph, and this function is so simple that we also can solve it analytically, but that may not be the case every time. So in that case, I use the formula and I get x2 is equal to 5 minus, you put the value fx, that means 5 minus 3 whole thing square, that means 2 whole thing square, which is 4, divided by 2 divided by f dash xn, that means 2x minus 3, x is 5 here, so 2, 5 minus 3, 2 into 2, which is 4 again. So 5 minus 4 by 4 is equal to 5 minus 1, which is equal to 4. So x2 is equal to 4, and graphically also you can see that once I have taken a tangent, the point at which it cuts is 4. So formula gives me 4. Graphically also I understand I have moved from 5 to a value 4, which is closer to 3. So what is my next step? I'll take a tangent at 4. That means this time it will be x3, and instead of x1 it will be x2, and I'll put the value 4 now. X2 is 4, I have already calculated, and f of x1 divided by f dash x1, that is a little mistake here. It should have been f of x2 divided by f dash x2. So I just copied and pasted from the earlier formula, so 1 remained there. It should have been x2 and x2 here. So this value will be 1 by 2 half. So 4 minus 1 by 2 is 3.5. So you can see graphically also we have reached a value 3.5. So now my next step will be to find the tangent at 3.5, and I'll see that I'll come even closer to the, actual value, actual root 3, and the process will continue. But as I have said, while doing by hand, we have to stop after a few steps. We cannot keep on doing. So let me stop here. Let me get satisfied with the value 3.5. Although the value is actually 3, which of course we know because we can solve this equation, which is the easy equation. If it is not an easy equation, we will not be able to solve it. But here, since we know the actual value is 3, I can say that 3.5 is okay, but still it is not the correct solution. We should have done few more steps. But since I am a human, I will not do few more steps. Had it been a computer program, it would have done, instead of x3, you would have done probably x100 or x1000, and you would have got a much better value. So they are the concept, or they are the importance of computer programming comes in doing numerical methods, because these numerical methods are basically repetitions. Just the way we get x2 from x1, we'll get x3 from x2, we'll get x4 from x3. While we do by hand, we have to repeat the things exactly the way we have done earlier. But if for a computer, repeating is not at all a problem. We can put a loop and it will keep on doing the things. Okay. My last topic, inverse of a matrix. Let me see how much time do I have. I have around 8 minutes or so. I will be able to finish. Okay. So let us take a identity matrix 1001. Let us do a row operation. Row operation, a simple row operation is multiply the first row with 2, so that becomes 2 0 and 0 1. This new matrix which I have got from the identity matrix is called an elementary matrix because it was obtained by a row operation. So that is an elementary matrix. Now there is a very important thing about this elementary matrix. The moment you multiply an elementary matrix with another matrix, so 0, 1, 2, 3, the result that you will get is same as doing the row operation which was used to get the elementary matrix on this new matrix 0, 1, 2, 3. You will get the same result 0, 2, 2, 3, 0, 2, 2, 3. So I repeat, row operation on a matrix is nothing but pre-multiplication by elementary matrix. Both will give the same result. Okay. Now, once we have understood it, let us try to solve this equation. So I can write this in matrix form: 4, 9, 2, 3, xy, 13, 5, the column matrix. I can write 4, 9, 2, 3. I can take 4, 9, 2, 3 to the right hand side. It becomes inverse. And actually, I do not take it to the right hand side. I actually pre-multiply with the inverse of 4, 9, 2, 3, both on the left hand side and right hand side. And that's how we get this result. So inverse multiplied by the same matrix gives me 1, or identity matrix. And on the right hand side, I'll have 4, 9, 2, 3 inverse. So if I can get the inverse of this matrix, I immediately can multiply 13, 5 column matrix to it, and I'll get the value of x and y. I have only shown it for two simultaneous equation with 2 variables. It can be done for any number of variables. For 2 variables, we actually need not do so many complicated things. But again, as I have done for earlier cases also, we have taken a simpler example to understand a process which can be used for complicated calculations. Okay, so main purpose is to find out the inverse of this matrix 4, 9, 2, 3. Once I have found the inverse of this matrix, then I can multiply 13 and 5 column matrix to it. I'll get xy value. So how to find the inverse of this matrix? One process is the cofactor matrix, adjoint of cofactor matrix divided by the modulus of A, the main formula, the well-known formula for inverse calculation that we have. And another method that we'll do here is a numerical method, so the computer can do the things for us. This is for the computer to do. If we do by hand, and if it is a smaller matrix, we can use our well-known formula. Inverse of A is an adjoint of A divided by modulus of A. Adjoint of A is nothing but transpose of cofactor of A divided by modulus of A is the inverse. But here we'll not use that formula because that formula is not used, that cannot be used by computer programs. So we'll use some other methods. This is actually called Gauss-Jordan elimination method. I'll show you. So I write A is equal to IA. I can always write A is equal to identity into A, and then do some raw operations on A. And if I do some raw operations on A, I have to do similar raw operations on I. If I do some raw operations in A, I have to do a similar raw operation in I. Why? Because raw operation is nothing but pre-multiplication by a matrix. So if I pre-multiply A by a matrix, here if I pre-multiply, that means the multiplication will be with I. That's why if I do a raw operation on A, I have to do a raw operation on I. I hope that point is clear. I have written A is equal to IA, something like X is equal to 1X. Then I do some raw operation on A, and I have to do same raw operation on I to maintain the equality sign. This is because raw operation is nothing but a pre-multiplication. So if I am pre-multiplying A, I have to pre-multiply IA also. If I pre-multiply IA, that means my multiplication is done with respect to I. That's why the raw operation is also with respect to I. So corresponding raw operation will be with I, and here also there should be raw operation with A. And ultimately, by doing some significant number of raw operations, I can change A to I, and in that process, I on which same raw operations were being done will become B. So this equation will become I is equal to B into A, and that will mean that B is nothing but inverse of A, because only inverse of A multiplied by A will be I, identity matrix. So B has to be equal to inverse of A. So that is the principle. So let us take the matrix. I am taking a general matrix, not 4, 9, and 2, 3 in this case. So if we have to instruct the computer, I cannot instruct it for a general value of 4, 9, and 2, 3. I have to instruct it. I mean, I cannot instruct it for a specific value of 4, 9, and 2, 3. I have to instruct it for a general sets of element. So here the elements are 1, 1, 1, 2, 2, 1, 2, 2. Now let me do a raw operation. R2 is equal to R2 minus A22 divided by A11 multiplied by R1. So immediately you can see the third element, A21 becomes 0, because A21 minus A21 divided by A11 into R1 first element is A11. So A11 gets cancelled. So R2 is equal to A21 minus A21, that is 0. So this becomes 0. And A22 of course will change to A22 dash. And I can use this raw operation again, and this will become, now the second element will become 0. Okay. Next what we do, we divide the first row by A11 dash and second row by A22 dash. So once I divide 0 by anything, it is 0. And once I divide A11 dash by A11 dash, this is 1. And if I divide A22 dash by A22 dash, this is also 1. So I get identity matrix. So if these raw operations are done on the identity matrix, because I have to do same raw operation on A as well as the identity matrix. A has already become identity. Now if I do this same operations on identity, that matrix will be the inverse. So I have to do the same operations on the identity matrix, and that of matrix will become inverse. So now let us take this example. I write the matrix A and the identity matrix, and as I have said, I'll do the same raw operation on both A and I. I'll change A to I, and in that process I will change to inverse of A, that is B. So first I'll write R2 is equal to R2 minus half R1. You can see here A21 divided by A11. In this case A21 is 2. and A11 is 4, so 2 by 4 is half, so I write half R1. And if we do this calculation, if you do this row operation, immediately you get 490 minus 1.5, and this side, the identity matrix will also change to 1 and minus half 0, 1. Next, I do R1 changing to R1 plus 6 R2. Immediately you get 400 minus 1.5, and my identity matrix, my initial identity matrix also changes to another matrix. Then I do the last step. R1 is equal to R1 divided by A11 dash. In this case, A11 dash is 4, and here it is minus 1.5. Immediately I get this A matrix changing to identity, and the identity matrix changing to B. And we have already said this B is nothing but A inverse, because only A inverse multiplied by A can be identity. So B has to be equal to A inverse. So this matrix is A inverse. So we have found out the matrix A inverse. Once we have found out matrix A inverse, then of course the things are very simple. I can just write A inverse matrix, multiply with 13 and 5. Immediately I get 1, 1. That means x is equal to 1, y is equal to 1. And that is the solution. You can see if I put x is equal to 1, y is equal to 1, I get 13 from the first equation. From the second equation also, if I put x is equal to 1, y is equal to 1, I get 5. So the solution is actually x is equal to 1, y is equal to 1. So this is the way we can get the inverse numerically. We have to define some steps and we can get the inverse. You can see we have got the inverse by changing my actual matrix A to an identity matrix. That means all elements other than the diagonal elements, all the off-diagonal elements are 0 and the diagonal elements are 1. I have done the row operations in such a way that I get identity matrix. This process is called Gauss-Jordan elimination method. There is a way, in fact, it is a simpler way to make only the lower triangular matrix 0 and upper triangular matrix will not be 0. Here both upper and lower triangular matrix are 0. I can make only lower triangular matrix 0. That should be very simple. Then making both lower and upper triangular matrix 0. And that process is called Gauss elimination method. So I have shown you Gauss-Jordan elimination method. Gauss elimination method should be even simpler than that. With this, I have covered numerical differentiation, numerical integration, solution of transcendental equation by bisection method and Newton-Raphson method, and also to get how to get an inverse by numerical method. And in that process, we have understood what is the concept of Gauss-Jordan elimination method and Gauss elimination method. So thank you. If you have any question, I'd be happy to take the questions. Is there any question?
Yes, participants, if you have any questions, you can ask Sir Samrat now. If you don't have any,
either my presentation was too good or it was too bad. So
either that's a good one,
or which I believe they must have, or probably they know the things already. That is another thing. Or probably, or otherwise they have not understood anything. Very less probable, I think.
Anyway, since we don't have any question, on behalf of the organizing committee as well as the participants, we thank the speaker, Dr. Samrat, for explaining the concepts of numerical analysis in a very simple and graphical way, which helps us to understand a lot. So moving ahead, we will go to the next topic, next talk, which is physical computations in Python. So may I request Mr. Parag Bhattacharya to please take on the session.
Okay, thank you, Amma. Just give me a couple of minutes. I'll just pull out where we had stopped because some little bit was left from yesterday's topics. So let me just pull up those notebooks. Give me a couple of minutes.
Should we give a break of 5 minutes for?
Yeah, I think that will be good. So 5 minutes break, I think will be
Let us
good.
break for only 5 minutes.
Yeah, yeah,
We'll join in the same link.
yeah.
Samrat, there is a question.
Yes,
In the
I can
meantime, you
answer
can
it.
just, yeah. All the participants who would like to take a break, yeah, you can just take a break for 5 minutes. Maybe we will meet at 11:15. Is it okay, Samrat?
Yeah,
Now it
that's
is around
fine.
11 at, yeah, we'll meet at 11:15, okay? But any one of you, if you have questions and want
Yes,
to
you can
join the
interact. I think
discussion,
it is
you
not a
can stay and
question.
yeah.
That was an appreciation. Thank you so much.
Okay.
panic attack হৈ গৈছিল panic attack এটা মানে কোনটো ডকুমেন্ট মই নেক্সট কৰি পাহৰি গৈছিলোঁ আৰু দুখন ডকুমেন্ট আছে চন্দাকে দিব প্ৰথমটো 10টা পেজ তাৰপিছত 8টা পেজ Good morning, everyone. Auma, can we start? Auma, can you hear me?
Okay, welcome back. So let us start the session again. So may I invite the speaker, Mr. Parag Bhattacharya, to start the second session of the second talk of the technical session 2 on the topic of physical computations in Python. Mr. Parag.
Yeah, thank you, Auma. We will carry forward from where we had stopped yesterday. We had done till the range function. And then I'll talk about user-defined functions today. Okay, so user-defined functions, they're in every programming language. Okay, we have this facility to provide user-defined functions, So basically, it gives a way for us to process, to execute, for the program to execute a collection of statements. So a user-defined function, basically, you take a lot of statements, you collect them together as a single block, and you can execute that as a block anywhere in the program. Now, in a function, now there are two things that we need to keep in mind. One is the argument, another one is the return value. Those who have done programming, they will know what I'm talking about. Arguments are the values that you're passing to the function. You are sending some values to the function, and the return value is what the function is passing back. Now, a function need not always have this your arguments and return value. There could be functions which which have neither have any arguments nor do they have any return value. So that is also possible. So in Python, this is how a function block looks like. Okay, so this is the syntax of a function block in Python. In Python, the function is specified by this keyword called as def, def. Def means definition. They don't call it function, they call it definition. So def is a keyword which is used to specify that we are talking about a function. So this is how the syntax of a function looks like. So we have def and then the name of a function. So this is an identifier. Whatever are the rules that is applicable for naming of variables, the same rules are applicable for the naming of functions also. Then we have arguments. This is a set of values that you are passing to the function. Okay, so they're called as the arguments. And then inside this, we have these different statements. Okay, and all of these statements, because the function is also a block, the same rule for a block, it also holds good here. That means the block statement, def name, def function name arguments, that is the block statement. It must end with a colon, and the moment it ends with a colon, that means at least one line must be indented. So the indentation rule holds good here also. And then all these lines which are indented, they become the function body. And these are what are executed when the function is being called. And the last line of the function could be something like a return value. Now a function need not always have a return value. Okay, so this is the value it is passed. So suppose I'm passing, let's say x, y, z. Okay, and then it is just adding up. Okay, the return value will be simply x plus y plus z. So that is the value when it is going to be passed back by the function. So now let's just see a simple function. Okay, very simple function. So let me just define a function. So def, let's say WCP. Okay, I call it as def WCP. All that it is going to do is it is just going to print out two messages. That's all it's going to do. So print welcome to workshop on computational physics. This is one statement. This is one function statement, and the other function statement print. You see, by default, this Jupyter notebook, it already does the indentation. The moment I put a colon and when I press enter, it starts with an indented line. Okay, so you don't have to worry about indentation in when you're working with Jupyter notebook. Then let's just put another line. Say organized by the Department of Physics, ADBU. Okay, so this is one function. So now let's say I want to use this function. So all I need to do is I just have to write WCP. That's all. And when I run this, you find whatever is there inside this. First, it is going to print this line. Then it is going to print the other line. Okay. So now I could have, let's say, another function, similar function, another similar function. Let me define another similar function. This other function, I'll call it as addition. Okay, so here I'm going to take an argument. The argument is the year. Okay, the argument is the year, and what I'm going to do is I'm going to put this at the end. Okay, in the print command, I'll put this here, whatever I'm passing here, whatever value I'm passing here, that value gets printed out over here. Okay, that value gets printed out over here, and then let me just call this function after this. So WCP underscore addition. And here I have to give an argument. If I try to run this, I'll get an error. I'll get an error because it's saying that it requires an argument. It requires a positional argument here. So I have not given any argument. I'm calling this WCP addition, this function, but I have not given any argument here. Because I have not given any argument here, it's telling me, it's complaining, and it's telling me that there is an error. So let me give some argument here. So this here 2020. Now if I run this, now this is going to show me accurately. So whatever I have passed in, okay, it will be appended to the workshop on computational physics. If I change this, right, let's say like after 10 years, let's say this workshop is still going on after 10 years, then it becomes 2030. So now this function, okay, this function, it can be used anytime, even after 100 years also. So those people after 100 years who are running the Department of Physics at ADBU, they'll be able to still use this function. Okay, so I by putting this, by giving some, providing some the facility for passing an argument, I have made this function, I have made this more general. So you can actually customize your function the way you want it. You can customize this using whatever you want, using the arguments. Okay, next let's do another one. This is a very simple function. Let's do another function. So over here, the same thing. Okay, we had done this cooling law. Remember, if you remember, we had done this cooling law. I think the program will be somewhere over here. Yeah, this is the program. We had done this earlier. This is the cooling law program where we had calculated. This was the calculation that we had made. This was the calculation that we had made here. So what we can do is this calculation part, I could just put it inside a function. Okay, this calculation I can just put inside a function. So we just go ahead and copy this from this entire code that we had written yesterday, and let me just place it over here. Okay, so now what I'm going to do is I'm going to execute this part. I'm going to execute it elsewhere. Okay, this part I'm going to execute it using a function. So let me just copy this part. I'll copy this part, and then I'll just replace this with, let's say, cooling law. I call this function as cooling law. Okay, the arguments, I'm going to put the arguments a little later. Let me first define the function. So I'll go right till the top, the very beginning of the code. Okay, and in the beginning of the code itself here, I will put this because I want to know what the formula is. So what I'm going to do is, now I'm going to define this function. What is the name of the function? The name of the function is cooling law. Okay, the name of the function is cooling law. So name should be exactly the same. Okay, you cannot simply, suddenly if you put a capital L here, then this is going to be an error, because like I said, the same rules which you follow for naming your variables, the same rule also you have to follow when you are naming functions. Okay, so cooling law. Okay, so now let's write down the code. Okay, so what it is going to do is, it is just going to calculate, and it's going to calculate some value of t, and it is going to return the value of t. But now this function is not going to work, because this definition, it does not know what are these quantities, because inside this block, these are local variables, capital T environment, T0, all these are local variables. That is, these are the variables which are available only inside this function. They are not available outside. Okay, so it doesn't really know what are these variables. So one thing that I can do is, I could just pass these as an argument. So one of the arguments is time, right? So I could just put time as one argument. Then another argument is the initial temperature of the body, so that I could put as another argument. Then another argument is the T environment, right? So I could pass that as an argument. Then another argument is the tau. You could pass this also, right? You could pass this also as an argument. Now also one more thing that I notice here is this math, right? This exp function that I'm importing from math, right? So I could just if I could do this importing of this function, I could do it from inside the function definition itself. Okay, so I could just put this over here, and or I could also put it like, from math, like import math, and then I could just put math.exp. I could do that also. So this becomes a function. Okay, this becomes a function that we have written here. Now if I execute this, it will still give me an error, because I have not passed any arguments here to cooling law. Okay, I have not passed any arguments, so I have to pass the same arguments. So let me just copy the arguments from here, and then put them here, and let me run this. Initial temperature, let's say 100 degrees centigrade. The ambient temperature, let's say, is 16 degrees centigrade. Then the time constant, let's say 600. So it's giving me the table that I am expecting. So what is basically happening here is this code, it knows that there is a function called as cooling law. Then the rest of it till here, till it does as before. It creates the initial time and final time, number of divisions, then number of samples of time that we need to take, then the delta t. Then it creates variables. It takes from the user. It takes from the user what is going to be the initial temperature, the ambient temperature, and the time constant. Then it just draws these lines, and then inside the for loop, this is where the action is happening. Inside the for loop, this cooling law function is being called. So the moment the Python encounters this line, it sees that okay, there's something called as a cooling law, and it already knows that yes, there is a function called as cooling law. There is a function called as cooling law. So what it is going to do is these variables that I have passed inside this, okay, in the same order, t. Okay, it will match it over here, t, then t0, t environment, and tau. It is going to just pass. So this value of t will go here, this value of t0 will go here, this value of the ambient temperature will go here, and this value of tau will go over here. And then it will do this calculation, and whatever result it gets, it will return to the right hand side. The right hand side will get replaced with whatever is the result. So that result will be the value of this t, and then it will just print it out, and that's how we are able to get this. Okay, so this is how a function works. Now also one more thing, you would have noticed here that I have used these variables, no, the variables that I have used here, t, t0, t environment, tau, and here also the variables are same. They need not be same. Okay, the variables need not be same. I might as well call it as a. This small t, I could just call it as a. That means here also I have to replace the small t, I replace it a. Similarly, t0, I could call it as b, and here I have to simultaneously I have to replace it with b. Then t environment, I could call it as c. Okay, and here also inside I'll have to replace it with c, and here also there is a t environment, I'll replace it with c. And tau, I could call it as d, and here I replace tau with d. This is also going to work. Okay, in fact the return value also need not be of the same name. Return value I could just call it as x, and it is going to return x. Okay, because these values, like I said, these variables, they exist only inside this function. So it really does not matter. Only what matters is the formula. The formula should matter. Then only it's going to give the result that I am looking for. So now this is also going to work. So when I run this, you will find that the result is going to be just the same. So let me just run this once. So 95, let's say 25 and 900. You see, again we are getting the same table. It's working perfectly fine. Okay, so you can give the the naming of the arguments. It need not be exactly the same as what you're using, but it helps the readability. If you're doing this, I always use the same names. Whatever names I'm using in the function call, the same names I use in the function definition also, because that helps me to actually understand what's happening. So that's about how that's a couple of examples of how to create this how to define a function. Okay, so now let's look at we'll look at the types of function arguments. There are mainly three types of function arguments. First type is known as positional arguments. Okay, and positional arguments, there is one more variation that is called as variable length positional arguments. Next type is a keyword arguments. Another variation of this is variable length keyword arguments. The last one is default arguments. In this workshop, I'll be giving demonstration only of the positional arguments, the keyword arguments, and the default arguments. That's all I'm going to be talking about. I'm not going into details of variable length arguments for positional and keyword. Okay, so if you are interested, I could provide you enough resources where you can actually read up and read, but these are basically advanced topics working with variable length. So we are going to focus on positional arguments. Okay, so what are positional arguments? Positional arguments, they are the most common. So over here what happens is the values are simply copied to their corresponding parameters in order. So what has happened here is these are positional arguments. The arguments that I have given here, these are positional arguments. Okay, so whatever values I'm passing on, this A must be mapped to T. Okay, then this B must be mapped to T0, C must be mapped to T environment, and D must be mapped to tau. If I change the order, okay, if I change this order, let's say I make this as tau, the first argument I'm sending it as tau, and the last argument I'm sending it as T. Okay, then what is going to happen is this A is going to become tau, and D is going to take the value T, and as a result, the formula will be e to the power minus tau by T, which we know is not correct. So if we run this, 95, 26, 600. You see, I'm getting some zero division error. Some error is coming here. The zero division error because the time that I'm starting here, the time I'm starting from t equals 0. So that's why. So let me just change this and make this as 10. Okay, let's see. That should avoid the zero division error. 95, 26, 500. Okay, it is giving me some values, but this is not what we are expecting. This is not how cooling works, right? It is telling me that the initial temperature of the body is 26, which is not true. I have given initial temperature to be 95, so it should be starting from 95, not 26. Okay, it is starting at the ambient temperature, and then it is saying that its temperature is increasing. This is not how cooling works. Physically, this is not how cooling works. What is the reason for that? Reason is I have made an error here. I have first put tau and then I have put t, whereas in the function definition, first I should put the first argument should be t and the last argument must be tau. Then only it is going to work. Okay, now when I run this, 95, 26, 800. Okay, now you see it's starting, right? 93. I mean, the starting temperature is starting time is not 0, it is 10. If I put it as 0 starting time, if I put it as 0, then it's going to show it is going to start at 95. 16, 900. It's going to start from 95 and so on. Now this is now it is more correct. Okay, now we know that yes, its temperature is decreasing. So this is how cooling is working. So this is an example of actually positional arguments. Example of positional arguments. So one example that we have this one this Rydberg's formula problem. Okay. So when a lone electron in a hydrogen-like atom, it undergoes a transition between two energy levels, and these two energy levels.
Sir, your voice is cracking.
Pardon? Is this a problem with everybody?
Sir, your voice was cracking.
Okay, is this the problem with everyone?
No, sir.
Samrat?
Yes, sir.
Okay, then that must be probably okay. That might be probably the individual internet connection. Okay, so if you have missed out some part in the recording, it will be fine. So you can just catch up with that in the recording. If in case there's a audio problem, like
Okay, sir.
everyone, just let me know. Okay, if more people have, then probably the problem is on my side. Okay, so now coming to this one. So when suppose a lone electron in a hydrogen-like atom, it undergoes a transition between energy levels, between levels N1 and N2, with N1 less than N2, then a photon is either emitted, okay, in case the transition is from N2 to N1, or it is emitted, it is absorbed. It is absorbed in case it is from N1 to N2. In either case, there is going to be a wavelength of the photon, and this wavelength is given by the Rydberg's formula. You all already know the Rydberg's formula. So 1 by lambda is equal to RZ square 1 by N1 square minus 1 by N2 square, where Z is the atomic number of the element and R is the universal constant, which is known as the Rydberg's constant. Okay, so we want to do this. I think we had done this yesterday. No, not sure. Did we do this example? If it's there, then I can just take the code from there. No, we have not done this. Okay, so we can just go ahead and we can write this. Okay, just a few lines there. So what I'm going to first do is I'm going to define a function. That function is going to calculate this, do this calculation for me. So I could call it, I could use a def, and the function name is Rydberg. I'll call this function as Rydberg. Then I could have some arguments. The argument name should make sense to me. So first argument is atomic number, atomic underscore NO. Never do this. Never do this. Don't put space because spaces are not allowed in the names of variables. If you want to use space, use underscore. Okay. Atomic underscore NO. Never use dash also. Dash is also not allowed in the name of a variable. So atomic underscore number. Then we have a lower level and we have upper level. Okay, and then we can start coding this. Okay, so what I'm going to first do is I'm going to define the universal constant. So R is equal to 1.09678. So 1.09678 times 10 to the power 7. So that I could just write it as E7, that is going to raise it to the power 7. Okay, now one more thing. Okay, the user could ask from the I mean the program could ask from the user the n1 and n2 values, but there is a chance, because the requirement is n1 must be less than n2. So there is a chance that by mistake I could enter n1 greater than n2. I could enter n1 as 2 and n2 as 1. So in that case, this formula is not going to work. So how do I ensure that that does not happen? I could do some bit of coding inside this definition itself. So what I'm going to do is I'm going to ensure that this lower will always be the smaller value and upper will be always the larger value. And the way to do that is I could use if condition. Okay, the if condition is, there's only one condition that I have to check. The condition is, if by chance the lower level that I have given, it happens to be the greater than the upper level. Okay, if by chance the lower level is greater than the upper level, then what should I do? I should just swap the values. Okay, so if say lower level I have given as 3 and upper level I have given as 1, then lower level should be 1 and upper level should be 3. So I can just swap the values, and you all know how to swap, right? Lower comma upper is equal to upper comma lower. So this is I'm doing multiple assignments in the same line, so you can do the swapping part. So this if condition will only be it will only execute this line when the lower level is by mistake you have supplied a lower level which is having numerically larger than the upper level. Only then it is going to be executed. Okay, so we give this if condition. Next, what we need to do is we need to calculate this. Once we are done with this, now this is going to be sure. Now after this step, we are 100% sure that the lower level will always be less than the upper level. So now I can just go ahead and calculate this. So first I'm going to calculate this quantity. This quantity I'll call this, because there is a r here and there is a z square. Okay, and then this is multiplied, this r into z square. Okay, there is no z square. I'm using atomic number here. So r into atomic number. Make sure that this matches. So in order to make sure, just always copy this from the argument and paste this here. By mistake, you make some change here, then that is going to lead to an error. We have to take the square of this. So r into atomic number square times we can see from the exoskeleton of this formula, there is a bracket. Okay, and inside this bracket there is a difference of two terms, so something minus something. So always make the exoskeleton of your formula first, like this. Okay, so r into atomic number square into, inside the bracket we have something minus something, and here I can now put. So first thing, what is the first thing? So first one is 1 divided by the lower level square. 1 divided by the lower level square. The second one is 1 divided by the upper level square. Okay, so we did this. So but this is just an expression. If you remember, this is only an expression. This is not a statement. For it to become a statement, I need to assign it to some variable. Okay, so for that, what I'm going to do is I'm going to create a variable. Okay, the variable is, because this is 1 by lambda, on the left hand side there is 1 by lambda, I can call it as INVLMDA. This is inverse lambda. Okay, so what I have calculated here is inverse lambda. Okay, or I could just call it as, because inverse lambda is wave number. Wave number is equal to r into z square into 1 by n1 square minus 1 by n2 square. So what we have calculated here is the wave number, and as a result, the wavelength. You can see the names that I'm giving here. The names are those names which have some meaning for me. The wavelength will be simply 1 divided by the wave number. Okay, the wavelength will be simply 1 divided by the wave number. And once we are done with this, then we could just return the wavelength. Okay, so this will give me the wavelength. Remember, this will give me the wavelength in meters. Okay, this is going to give me the wavelength in meters. If you want to convert this, okay, if you want to convert this, let me call another function. Okay, meter let's say I want to convert this to nanometers. So meters to nanometers. Okay. So let's say I have a quantity X. I want to convert this into nanometers. So what we need to do is return X times nanometers. You have to multiply with 10 to the power 9. So 1e9. Okay. So this is going to give me the same value, whatever value I have given here, it is just going to convert this into nanometers. Okay. So 1 into 10 to the power 9. Then let's say I want the wavelength in angstroms. I could have another function, okay, meters to angstrom. So here I have to multiply this with 10. Okay, so we got all the functions that we needed. So now it's time to apply this. So what I'm going to do is z equals, we don't need float, we need int, because atomic number is always integer type. So take input from the user. So enter z. Enter z. Next, we'll say, let's say we call it as n1. Okay, n1, or just call it as m. So this will be integer type again. Input, enter a level, and the next one we call it as n. Enter another level. Then after this we just have to calculate the lambda. Lambda is equal to Rydberg. You can notice here I have used some value here. I'm just calling it as lambda, which is equal to the function Rydberg. Okay, the function is Rydberg, and here I'm going to pass. Now this is positional arguments. That means the order has to be maintained. So first will be z, then the next, it does not matter, lower and upper does not matter. I could put in any order because this if condition is going to take care. If I put a lower this one upper level first, doesn't matter. So we could just put as m n or n m. It's not going to matter much. So then after that, print, okay, the wavelength of the associated photon is, I could just put LMDA. Okay, let's just run this. So let's say we'll take hydrogen. So Z is equal to 1. So 1 and 3. Okay, the wavelength of the photon is this. Okay, now this doesn't look nice. We want to write this in, let's say, we want to write this in nanometers. Okay, so we want to write this in nanometers. So what we can do is I could just make the conversion here. So delete this, and we will use this one, this function, meters underscore 2 nanometers, and here I'm going to put the lambda. Okay, so let's run this. 1 1 3. Okay, so now it has given me the wavelength in nanometers. This is looking better. And then after this, of course, I could just, because I have to specify, I have to specify that this is actually nanometers. So it's just nanometers here. So 1 1 and 3, it's giving me this nanometers. But then I don't need so many decimal places. Okay? I don't need so many decimal places. Just one decimal place is enough. One decimal place is enough. So it means how many significant figures? At least 4 significant figures. Let's keep it as 5. Okay, let's keep the significant figures as 5. So 5 plus 1 is 6. Decimal places is 1. Okay, F this 1 1 and 3. Okay, so it is giving me the way I want this. In case you want to display this in terms of angstroms, you could do that as well. Here I just call this other function. This is meters to angstrom. Paste this over here, and then we can just put A here because I don't have a symbol for angstroms. Okay, this is giving me the wavelength that I want. Okay, so this is an example of positional arguments. Okay, next is something known as a keyword arguments. Okay, keyword arguments, what happens is the arguments, they're not matched by name, they're matched by name, not by position. The arguments, they're matched by name and they're not matched by position. Okay, So we'll take the same example. Let me just copy the code from here. Okay, so now how do I, pass on positional arguments? How do I pass on positional arguments? You could pass on positional arguments like this. Okay, you could pass on positional arguments like this. So here we'll just use whatever are the names that are given to the arguments. So we'll use something like this. First argument is atomic number. Okay, let me just copy the arguments from here. Atomic number, lower and upper, and let me just paste this here. Then what I'm going to do is I'm just going to say equal to Z. Atomic number is equal to Z, lower is equal to M, and upper is equal to N. Okay. And the moment I do that, now it is able to understand. When I pass this, it automatically understands which is related to what. So I can actually now change the order. Okay. So I could just put atomic number somewhere between lower and upper. Okay, but this is not how the function is. You see the order: first atomic number, then lower, and then upper. Right here, first I'm putting the lower level, then the atomic number, and then the upper. Let me run this. 1, 1, and 3. It's still working fine. Okay, so this is known as keyword arguments. Okay, so the arguments are matched by name and not by position. Okay. So you can, so here the order of the arguments does not matter. So it becomes more readable. So if I'm reading this, then I immediately get to know, okay, fine, this actually makes sense. The atomic number is Z and so on. If you send by mistake, if you pass some results, I mean, instead of atomic number being Z, if you say atomic number is equal to, let's say M, okay, so then you'll know exactly where the problem is. So this is known as the keyword arguments. Okay. So next is known as default arguments. Okay, and also one more thing, it is possible. It is possible for us to combine positional and keyword arguments in a single call. Actually, we can do that. Positional and keyword arguments in a single call. It is possible. Only requirement is we have to specify the positional arguments before the keyword arguments. So if I do something like this, okay, I want to specify the lower and the upper. Okay. I want to specify the lower and the upper. So what I can do is, first I have to specify the atomic number. Atomic number is Z. Okay. Okay. This is also going to work. Here I'm just combining. I'm just combining the this is an example of positional argument, and these two are the example of conditional arguments. Okay, so I can do that. The second and third, they are keyword arguments. So because the second and third are keyword arguments, they will always follow the position. So always positional arguments first, then keyword arguments. I could just change the order. Here it's lower and then upper, but I could just change the order here also. Now let's say I do something like this. Let's say lower level, I'm taking it as M, and the upper level is, let's say, N. If I say that, okay, first I'm going to put the keyword arguments, this is not going to work. Okay, it's going to give me an error. Positional argument always follows a keyword argument, so this is not allowed. Okay, let me just get back to the original one. Atomic number is equal to Z. Upper is equal to N, and lower, I'm changing the order, is equal to N. Okay, now it's going to be working just fine. Okay, so these are positional arguments and keyword arguments. Then there's something called as a default arguments. Default arguments, what happens is you can decide, you can decide some of the argument values beforehand itself. You can decide. So for instance, in this example, the same example, let me again copy these. Some of the values you can provide default values. You can provide default values. So let's see here. So let's say atomic number default value, I'm keeping it as 1. and that is hydrogen. Then lower level, I'm keeping default value as 1, and the upper level, I will keep the default value as 2. Okay, I do that. Now, when I run this, it's going to do the result will be exactly the same as earlier. Okay, the result will be exactly the same as earlier. As you can see here, nothing has happened. But just watch. Let me just remove all the arguments here. Let me remove all the arguments. You see, now it looks like as if I'm not passing any arguments. I'm not passing any arguments at all. Right? Okay, before we do that, let me just get these values. So this one, atomic number 1, 1, 2. So let me just run this with 1, 1, 2, 1, 1, and 2. Okay, the value is 1215 angstroms. The value is 1215 angstroms. 1215 angstroms. Now let me just remove all these. Okay, let me just remove all the arguments in the function call, and now I'm going to run this. Okay, I'm going to run this. It is asking me for some input. So 1, 1, and let's say I give 3. Okay, I'm expecting the value to be 900 something, but you see it is still giving me 1215 because 1215 is the whatever is it is going to be the value for z equals 1, then n1 equals 1, and n2 equal to 2. That calculation will give me 1215. So even though I have given some input, but here while calling the function, I have not provided any input. While calling the function, I have not provided any input. So because I have not provided any input, so it is just going to take the default values. Okay, it's just going to take the default values. Now you can also do something like this. Okay, let me just copy this thing, paste it here. Now let's say I want to change. Okay, atomic number is 1. Okay, lower level is 1, but you want to change the upper level. So you could do that. You could just pass on only the upper level. Okay, let's say I want to make it 4. Okay, and I want to run this 1, 1, and upper level. Okay, I'm putting some value here. Let's say 5. Okay. Now it is going to give me upper level. It is going to give me the value 4. It is not the whatever inputs I'm giving, that is not working at all. Okay, I could just give whatever I have given as the input. I could just provide this over here. Let's say I put this as n 1, 1, and let's say 4. Now it is calculating for upper level equals 4. It is calculating this. So I could just give if there are 3 arguments, out of these 3 arguments, because all 3 of them have default values, I could provide some of these. I could provide either at least one of these default values, or none of the default values, or all of the default values. Anything, all of the values I could provide. All of the arguments I could provide. So it's not going to cause any error at all. Okay. So like as before, you could actually mix together. You could mix the positional arguments, the keyword arguments, and the default arguments. That they can also be mixed. Okay. So again, when you're mixing this requirement has to be followed. First positional, then followed by the keyword arguments. Okay, always positional for arguments first. So that's about functions. So I suggest that you could just play around. You could just try out different functions. Whatever problem comes to your mind, just try out, and then write a function which does that. Okay. Next, we come to a very important topic, which is using packages. Okay, so packages, they are very important in Python because they, first of all, they provide us facilities for performing specialized tasks. There are some tasks which may not be possible for me or you to do. For instance, calculating sine. So how do you calculate sine? The sine of x. How do you actually calculate inside a computer, right? So how inside a computer, what happens is a Taylor series expansion is what is used, okay, for calculating the sine of any quantity. So now over there, that means moment there is an expansion, that means there is going to be some kind of a there has to be some kind of a approximation, because all series expansions, there has to be some kind of a approximation. So this approximation, all this is actually done, and it is already provided in some packages. So we have already imported some of these packages in some programs which I had shown you, but we'll do some more in detail now, then that will make more sense. Like for instance, here there is this package called as math. Okay, there is this package called as math. So what did we do? This math package has got a function called as exp. What this exp does is it calculates the e to the power x value. So whatever you're passing as the argument, it calculates e to the power that argument. That's all it does. And it returns that value, the result it returns. Now we can also write our own function, right? We can also write our own exponential function using the Taylor series expansion, but then that is not advisable because there is a chance that you might make some mistakes here and there, and then as a result your computations may not be as accurate as you want them to be. So that's where packages come into the picture. So packages, they provide these facilities. Okay, they provide specialized functions which can help you do tasks. They can provide variables, okay, which you can actually use in your program. For instance, the value pi. What's the value of pi, right? I mean, it does not terminate, no. So you can't simply calculate pi in your program. Suppose if I use 3.14, that is not going to be accurate. So if I need 4 or 5 decimal places, that is not going to be accurate. 3.14 will not be accurate. So the value of pi is already been calculated and it is already stored in the package called as math. It is also stored in the package called as numpy. So all I need to do is I just need to include that package and I can start using those variables and those functions in my own program. I could start using them. So this using of packages, it provides these facilities. I could do more specialized tasks without actually, defining those tasks myself. Okay, somebody else has defined it. I just go and use this. So those of you who are doing programming, let's say in C, C++, okay, in these languages, you would have probably included header files, right? In the beginning of the program itself, in C or C++, you use hash include and then you use the header file. In case of C, you use hash include iostream.h. In case of C++, you just use hash include iostream, right? So in case of C, this iostream.h, that's a header file, and that contains some of these procedures that you use for doing standard input and output. You cannot keep on defining them by your own, so you just include that header file and you use it. Similarly, C++ also, it provides this library called as iostream, and this iostream library, it gives you all the routines that you require for getting input and output. So packages are similar, very similar to that include command. In C, C++, include command, packages are very similar. Importing of packages in Python. Okay. So these packages, when we say they have a hierarchy, associated with them. First, we have at the topmost level, we have a package. Inside package, you could have many different modules. You will see an example of package having module when we do this plotting of different, plotting of different kinds of functions. So under package, you could have many different modules. Then inside one module, you could have different functions. Inside a module, you could have different functions. And inside the function, of course, we have these statements. Okay, so packages, modules, functions, and statements. This is the hierarchy that is followed. And inside a module also, you could have many different variables. Now, inside a package also directly, you could have functions. You need not have separate modules. I mean, you could have a package, and inside the package, the functions are defined or variables are defined. Okay, so this is basically how the package hierarchy works in Python. Now, some important Python packages for physics computations. One you have already seen, which is known as math. Then there is another very important package known as NumPy, numerical Python. That's what it stands for. We will see that next. Then there's a package for plotting data. Okay, in the afternoon probably we'll see that. This is known as matplotlib. Okay, and inside this this is what I'm talking about. Package and module. Matplotlib is the package. PyPlot is the module. So PyPlot is a module inside a package called as matplotlib, and this PyPlot contains all these functions for plotting your data. Then there's something called the SciPy and SymPy. SciPy, it contains routines for performing scientific computations, and SymPy is it contains routines which are very similar to language such as Mathematica. Okay, this symbolic languages, okay, such as Mathematica. SymPy actually does that. That's why it's called as SymPy for symbolic Python. Okay, and SciPy for scientific Python. In this workshop, we will be basically using these only: Math, NumPy, Matplotlib. These are the packages that we'll be using. Now, how to import packages? There are many different ways to import packages. First is a direct import. I just say that import NumPy. Okay, NumPy is a package. I just say import NumPy. By the way, this is a comment, so it is ignored. Then y is equal to, I want to, let's say, use the sine function. Inside NumPy, I have sine function. Okay, by the way, how do we check what is there inside a function? I'll show that first. So let us say I want to import math. Okay, how do I check what are the contents of a package? I could just use this dir function. It is going to show me the contents of the math package. So all I have to do is run this. It will show me what all are there in the math. Okay, so in the math package, there is arc cos, hyperbolic arc cos, arc sine, and so on. Then sine, cos, all of these functions, they are available. The gamma function, factorial, all these are available. So it is always good to have a look at what are the contents of a package. Okay, but this one is not. It is just providing to me as a list. So what I'm going to do is I'm just going to use another way to look at it. So for content in, I can use a for loop. For content in dir math, print content, it is also going to work. Okay, it's just going to show me nicely each and every name. It's going to show me. Okay, so this is how you can find out the contents of a package. So we could do this for NumPy also. We could do this for NumPy also. We could do this. Let me just add one more cell. Let's do the same thing for NumPy. And then I have to use NumPy here. Okay, so it's going to show me everything that is there inside NumPy. Okay, everything that is there inside NumPy. Lots and lots of functions are available for us to use inside NumPy. Okay, we'll see that later. So I could just call NumPy, and you can see here, if you go, you'll find it's in alphabetical order, so it's easy to find out. You'll find that there is a sine function. Yeah, here it is. NumPy also contains sine, math also contains sine. There is a difference. I'll tell you what the difference is a little later. So NumPy function, NumPy package, the NumPy package contains a function called as sine. So that means if I want to use this, all I have to do is numpy.sine. That's what I have to do. Okay, so that's how we can use this. So NumPy, inside NumPy, that is sine. So numpy.sine of this one, and then print the value. So it is going to print this value. Okay, now let's say some packages are there, their names are very big, like matplotlib, right? I want to access matplotlib.pyplot. So you can't keep on typing matplotlib.pyplot. So we can just use an alias. Alias is an alternate name. Similarly, you don't want to keep on typing NumPy everywhere. So instead of that, what you do is you give a new name to it. You call it as NP. Okay, so next, wherever in the program, in the code, wherever it sees NP, wherever Python sees NP, it is just going to understand that we are talking about NumPy. So this is also going to work. Okay, so np.sine. Okay, I can start using this now. Whatever are the contents of NumPy, I could just use NP as a alias or as an alternate name, and I could just continue to use this. So this is import using an alias. Then there's another method which, I mean, like hardly anybody uses, and that is using specific modules. That is, if you're importing just maybe one or two functions from a module, then no need to import the entire module. You can just import those specific functions. So you could just say, in that case, suppose from NumPy, I don't want to import everything. I just want to import the sine function. So what I do is from NumPy import sine. So this is importing specific modules or functions. So now I don't have to put this. I don't have to write numpy. No need to write, because sine, this function sine is already, it is a part of my function. So if I can directly just use sine here, and this is going to give me the result, okay, as we expect. Then suppose you want to import all the functions, everything that is there in NumPy without using alias or without indirect import. Then you can just put, instead of sine, you can just put a star here. Star means everything. So import all the modules. So here also it is going to work. But generally, if you want to import everything, this is usually what is recommended. Import using an alias. This is what we use, because when you import using alias, and then let's say in this case sine is there are two in the same program. Let's say I'm using math also, import math. Okay, from math import everything. Now the math package also has got a sine function. NumPy also has got a sine function. So in that case, how do you resolve between the two? It will be ambiguous. No, there's going to be ambiguity between which function you are trying to use. I'll tell you the difference between the sine and cos, the trigonometric function in the math package and the NumPy. In the math package, what happens is, if you want to calculate the sign and cos for one single number, the math package does that. But if you want to calculate sign or cos for a list of numbers or for an array of numbers, then we have to use the sign or cos which is there in the NumPy package. Okay, so that's the difference. So it's always good to use an alias, because then you can actually identify which package you're calling, the function from which package you're calling. So this is how to view the contents of a package. And yeah, similarly here, okay, I'm trying to import matplotlib.pyplot, this module, pyplot module from matplotlib. I'll just give this one alias called plt. Now all I need to do is, for content in dir of plt, print content. Okay, so this is going to give me everything that is there in matplotlib.pyplot module. So everything that is there, all the plot commands, everything that is there, it's going to be it's going to show me over here. And from there I'll get to know, okay, what are the functions, what are the things from this particular package that we can use. So this brings me to the end of the last remaining 1/3 that we had left. Okay, so before I move on to the next topic, I could have some, like, if you have any questions, I could get them clarified. Any questions? Okay, if there are no questions, then maybe I could move on to data structures. Data structure also, it's by like I had put it in this day 1 topic, but it's so, I mean, the reason is because the topics that I had picked up yesterday, they were quite huge. So I had put them in day 1, but I'm going to cover this today. This data structures, very important. If you're doing scientific computations, you need to know data structures. Okay. So what is a data structure? A definition is given here. A data structure is data structure is data organization, management, and storage format that enables efficient access and modification, which I'm sure does not make much sense to all of us. So below that, there is a much simpler definition of data structures. It is a collection of data values, the relationships between them, and the functions or operations that can be applied to the data. So I have a collection of data. Okay, and what kind of relationship that these collection of data have amongst them, and what kind of functions or operations I can apply to this data. So that is basically a data structure. So in Python, there are many different data structures: numbers, strings. Numbers we have already seen. Strings, list, tuples, dictionaries. We will see this one by one. Numbers we have already seen, so I'm not going to spend much time in this. So we have, numbers could be integers, floating point, or complex numbers. So you could have integers, they could be positive or negative whole numbers, right? Then integers can be written either in decimal, binary, octal, or hexadecimal. Okay, so you can actually write down hexadecimal also in case of, if you want to express a number, an integer, if you want to express this as, let's say, binary or as hexadecimal, you could actually do that. Okay, so let me just show that once. So you just have to use this prefix. Let me show you how. Okay, so let us say I want to print a binary. Okay, I want to print a binary number. Print a binary quantity. I don't know what really is. So let's say I have a binary number. So 0 0 1 1 1 0 1 0 1 1 1 0. Okay, so let's say I have a binary number like this. I really don't know what is its decimal equivalent. Okay, if I run this, okay, it's giving me some error here. Okay, because why is it giving me an error? Because you see, it is thinking that I am trying to print the value of a variable. Okay, and then it is seeing the very first character in the name of the variable is 0. 0 is a number, and you know that numbers are not allowed. You don't allow numbers as you don't start the name of a variable with numbers. So it gives me immediately, gives me an error. So what I have to do is, because it's binary, you look at the prefix. The prefix is 0B or 0 capital B. So if I put 0B, okay, now the red color has gone. Now it understands, it sees the prefix 0B, then it knows, okay, whatever is next, that is 0 1 1 1 0 1 0 1 1 1 0, that is basically a binary number. So it is just going to print out the decimal equivalent. So you can quickly get the decimal equivalent in this way. So you could also have, print Instead of small b, you could put a capital B also. Both of them will work. It really does not matter. So let me give some other number. 10. Okay. So 1397. That's the binary decimal equivalent. Okay. So you could also have octal. In octal also you can actually specify. So print in octal. In octal, what you have to do is you have to prefix with 0 You have to prefix with 0 Okay. Then after that you can give octal. But octal, you have to remember that there are only 8 symbols. That is 0 to 7. So you cannot use 9 or 8. These two symbols you cannot use. So you could have something like this: 1, 6. Right. This is an octal number. Okay. When I do this, then immediately we get the output. This is the decimal equivalent. Similarly, instead of small letter O, I could put capital letter O. Okay. Then this is going to give me the decimal equivalent of the octal quantity here. Then you could also have hexadecimal. Hexadecimal means 0 to 9 and A, B, C, D, E, F. Those are allowed, right? So print hexadecimal. For hexadecimal, it is 0x and then followed by whatever you want. Okay. A, F. Okay, this is going to be a big number. B. Okay, let's say this number. So this is the decimal equivalent. Okay. Similarly, you could, instead of having small x, you could have capital X also. Some other number. Okay, so this is going to give me the decimal equivalent of this hexadecimal. Okay, so you could do all of that. Then you could have Boolean values also. Okay, there are also integers only. Boolean values, you could do it like this. So you could do something like A equals true. You could just say true, or B equals false. Okay, print A comma B. Okay, so true and false. These are not strings. These are not strings. These are booleans, because in case you see print, if you want to see the type, if you want to see the type of A, okay, it says it's boolean. BOOL means it's boolean. So boolean is also integer type. Then coming to floating point numbers. Floating point numbers, it could be positive or real numbers with or without the fractional part. You are already aware of this. Then you could also express these in scientific notation. Okay, you could express this in scientific notation. I showed you how to do that. So let's say I have A equals 4. A equals 4.5 E3. A equals 4.5 E3. Then print A. This is going to give us 4,500. Okay, then let's say we have B equals 13.65 E minus 2, and then I say print B. Okay, 0.1365. So you can express, this is how you express using scientific notation. Okay, then complex numbers. Complex numbers. So for complex numbers, we can obtain the real and the imaginary part. Okay, the complex number here we have to use J. I already showed you how to write complex numbers. Then the real and imaginary parts, they can be extracted using dot real and dot imag. So you have seen that also yesterday. I had done that. I will go to strings, because strings are important, because we use strings to give more meaning to our output. So strings, we could have this either it could be single quotes or it could be double quotes. So you could have something like WCP equals, okay, workshop on computational physics. Okay, and I can create another string. I could have a double quotes also, no problem. 3 to 5 December 2020. Okay, so even though in the first case I have to use single quotes, and the second case I put double quotes, Python doesn't make any distinction, so it just treats both of them as strings only. So print WCP and print date. Okay, so this is going to print whatever is the string. Then you could also have multi-line strings. Okay, you could have strings which could have multiple lines. So for multi-line strings, you need triple quotes, triple single quotes, or triple double quotes. So I could have something like this. Let me just take this example. So let's say WCP underscore 2020, the WCP underscore 2020, I create this variable. So I want this to span two lines. I want this to span two lines. So how we are going to do that is like this. I just put, triple quotes here, and do not put any quotes here. Then go to the next line, and then I'll just indent it so that it's easy to read. And I'll end this with triple quotes. Okay, so this is the starting and this is the ending. It knows whenever it says triple quotes, it starts with a triple quotes until it reaches the next triple quotes. Whatever is there in between, it is considered as a multi-line string. So now I could just print this, print WCP 2020. So it's going to show me, okay, it includes a tab also. If you don't want a tab, so you can just start from here. Okay, so it is going to give me in two lines. You can actually have the string. Okay, so now there's another useful way. You can actually convert any object in Python. You can convert this into a string. This is using what is known as a string str constructor. This is known as a str constructor. So how we can do that is basically this. So let's say I have a is equal to 89. So you know that a will be stored as a integer, right? So now s1, it's a s underscore a. Okay, now let's see if I just see type of a. Okay, if I do this, type of a is int. Okay, let me just take a print out properly. Print type of a is type integer. Okay, so next, let's say I create another string s underscore a. So what I'm going to do is I'm going to convert this a into a string. I'm going to convert a into a string, and then I'm going to print. First of all, I'm going to print sa. Okay, first let me just print a. Okay. Okay, first what I have done is I have printed a, then I have printed s underscore a. In both cases, the output seems to look exactly the same. But when I do type, when I try to output the type a, let me add here itself, is of type, a is of type a, and here I just add is of type of s underscore a. And I can see here the first 89 that it has printed, it is of type int, and the second 89 that it has printed, it is of type string. So this line, what it has done is, it has whatever input I have given, it has just converted that into a string, and it has given me that as the output. So you can actually convert, you could convert an integer type into a string. So you can do that for any data type. You can convert a float also into a string. You can actually try that. So if I do, let's say 89 point, if I put a point here, okay, this is a float, okay, and then this is a string. Okay, you can actually convert this one complex number also. You could convert a complex number also into a string. So if I have a complex number like this, a is equal to 2 minus 3j. If I do that, right, this also gets converted. So first instance, whenever it's printing first, this is a complex number. Then when it is printing next, it becomes a string type. So you can actually convert any data type into a string, almost anything into a string. So that's about using the string constructor to convert almost any object into string. Okay. Next is indexing a string. Okay, so now suppose I want to access individual elements of a string. So how do I do that? We can do that using indexing. Indexing starts from 0, just like C++. Indexing always starts from 0. Then another difference between Python and C++ is Python allows you to do negative indexing. Okay, so let's say I have something like this. Let's say I have let me just give this example. So So let us say I have some text. Okay, that text is, I'll just use the same values A to I, A, B, C, D, E, F, G, H, I. Okay, let's say this is the text. Okay, so over here I can access individual members. Okay, let me just call this capital T. Capital T, if I say capital T of 0, okay, capital T of 0, it is going to give me the value A, capital T, and whatever is the index here. This is the positive index, this index is 0. So it is just going to give me whatever is the value that is stored over here, that is A. Then if I give, let's say, I want to display, let's say F, I want to display F. So I could do it this way, 5, because, sorry, I'll say 5, because F, what is the index? The index is 5. So it is going to display F here. Okay, so I could do this, do the indexing this way. So let me just do it formally here. Print T 0, and next one will be print T 5. Okay, print T0, it is going to print A, and print T5, it is going to print F. Okay, now you could also have, you know, you could also have negative indexing. Okay, negative indexing, if I put negative values, it always starts from the end. Positive indices starts from the first, from left to right. Negative indices indexing, it always starts from right to left. So if I could do something like this, print T minus 2, if I do that, T minus 2, negative index minus 2 is H. If I put T minus 1, it is going to show me the last one. The last one is minus 1. Okay, last index is minus 1, where I is contained, so it is going to show me I. It is displayed I here. Okay, so this is how you can actually use positive and negative indexing to access each and every member of a string. So let's say why negative indexing is allowed is because suppose I have a long string and I don't know what is exactly the length of the string. I'm only interested in the let's say the last thing. You can do the slicing also. Okay, in this case for strings you can do slicing also. Let me just slicing. Yeah, I think I can do the slicing a little bit later here. Okay, this is accessing. Okay, so now strings are immutable. That means you cannot change the string. You cannot suddenly say that, okay, suppose I have a string called WCP. I want to change the quantity that is at the value which is at position 3. I want to change this. You can't do that. So for instance, let's say I want to say that T of 4. Okay, T of 4. What is there at T of 4? T of 4 is E. E was there. Let's say I want to change this. Okay, I want to make it small e. Okay, it is not going to allow that. I cannot do item assignment like this. This will be an error. Okay, so how do I actually do that? How do I actually do that? So I can do that this way. I can do it this way. If I want to change something, so what I can do is I could just have a temporary string. Okay, temporary string. That temporary string I could use whatever is the existing string. The existing string is I want T4. No, I want T4. So what I can do is I could just take everything from 0 to 4. Everything from 0 to 4. Let's just print this out and see. Print 10. Okay, print 10. Okay, because I have done slicing, I've taken A, B, C, D. From 0 to 4 means 0, 1, 2, 3, because 4 is not included. Okay, so it is going to take A, B, C, D. Then what I'm going to do is to this, I'm just going to add small e, and then I'm going to add the rest of this. The rest of this string is from 5 all the way till 8. 8 means 9. So T 5 all the way till 9. Okay, you see, now this has made the change here. Okay, so you could do it this way by creating a new string. You can actually do that, but you cannot change an existing string. You cannot actually do that. It's not allowed. Then slicing a string, you have already seen just now. Just now I have given an example of slicing a string. You can extract part of a string. You can extract part of a string using the slice operator. Let me show here. Let me create WCP is equal to workshop on computational physics. This is a string that I have created. Now I want to print only a part of this. Print WCP. Okay, it's going to give me the entire thing. Now if I say print WCP and then I put something like, let's say 3:10. Okay, what it is going to do is from 3, so 0, this is 0, this index is 0, this is 0, this is 1, this is 2. So 3 is, index 3 is k, 3, 4, 5, 6, 7, 8, 9. Okay, only till 9 it will go because stop value is 10. 10 is not included. So that's why it is showing me KSHOP space O. That's why it's showing me that. Okay, you could also, have indexing. You could also do it like this. You could have negative indexing also for if you want to do the slicing. So you have 3 minus 3. Okay, so it will start from 3 and the last index will be from minus 3. Minus 3 will be, this is minus 1, this is minus 1, minus 2, minus 3. So this I will not be included all the way till S, PHYS, till here it is going to extract. Okay, so you can extract parts of a string like this also. Then you could also do something like this. Print WCP. I could do something like this. 1, 10. Let's see what happens here. Okay, 1 to 10 is coming like this. Then if I put a colon 2, then it will take every 2 characters. After every 2 characters. So first it will take O, then it will skip the next one. It will go 2 spaces, 2 places. It will next take K. Then after that it will go 2 places. Then it will take H. After that it will take 2 spaces. It will take P. Then another two spaces. It will give us O. So the output of this one, when I write this line, the output of this line will be O, K, H, P, O. That should be the output. Okay. Yes, exactly. That is the output. So it just takes 2 characters at a time. After 2 places it goes and it extracts those. Okay. Then concatenating strings, you can actually join strings together using the concatenation operator, which is the plus operator. In this case, the plus means you are actually trying to add the strings. Okay, so let's say W is equal to workshop on, C is equal to computational, and P is equal to physics. Okay, then let's say I say something like this. I want to create a new string. That new string is W plus C plus P. Then if I say print WCP, okay, it is going to give me, oh sorry, S, there's going to be an S here. It's going to give me this, but it's just going to join this. So I have to give the spaces myself. Okay, or I could give the spaces here. I could give the spaces here in between. One space. Okay, let's see here. It has given some space here. After on and C, okay, there's going to be some space here. You could do the same thing. I could put some space here also. Now it is giving me the spaces here. So you can, this is known as concatenation of strings. Okay, there's another way to do that. The same thing, whatever I have done here, there's another way to do that. Let me just copy this code here. Let me just, okay, so we have WCP here. So one more way by which I can do that is like this. Okay, another way to do that is like this. First, W is equal to W. Okay, WCP is equal to W. Then WCP plus equals one space. Then WCP plus equals those modifiers. I'm using those modifiers plus WCP plus equals another space. And lastly, WCP plus equals P. Okay, this way also it is going to work. So, but this one is, suppose you are in a for loop, you're in a for loop and you're just, you're generating some words, some strings, and you want to add all of those strings together in a for loop. This way you can do that. You could just use plus, equals, and so on, the modifier. Okay. Next is finding the length of a string. Okay, you can find the length of a string using the len function. So I could have something like this. So print, let's say I want to find out the length of this same WCP. Its length is 33. Okay, there are 33 characters in this string. Okay, then you could replace specific text. Okay, you could replace specific text inside a string. Suppose I want to replace. Okay, let me just write this again here. I'll just get this, grab this from here. We can use the replace method to replace specific parts of the string. Okay, so I want to create a new string WPP. So let's say we have a workshop on particle physics. Let's say, okay, we have a workshop on particle physics. So I already have a string which says workshop on computational physics. So all I need to do is I need to remove this computational and I need to replace it with particle. Okay, so I create a new variable called as WPP. So what is this WPP? WPP will be equal to WCP. Okay, I'll take WCP, but I'm just going to replace. I'm just going to replace. You use this method called as replace. So first is the string that you're trying to replace. I'm trying to replace this computational. I'm trying to replace this computational. And what are you trying to replace this with? I'm trying to replace this with particle. Okay, so now if I say print WPP is going to give me workshop on particle physics. Okay. Next we have case conversion in strings. Case conversion in strings. You can change the case from uppercase. You can convert it into lowercase. Okay, so we have again. I'll just use the same thing, WCP. So if I say print, let's say I'll just keep WCP first. Okay, print WCP. Let me just grab this again because I want to change this a little bit. Because changing case means I need to do some modifications here. Okay, let's say in workshop on computational physics, what I do is this P, physics P that I'm putting in the small letters. Okay, now let me just print this is working perfectly. Okay, small letters is working perfectly. Okay, so now I want to print this. Let's print this. Print, okay, WCP, but this time WCP dot lower. And when I do that, everything becomes lowercase. W was capital earlier. This W was capital. It now becomes small letters. Then C was capital. It becomes small. Okay. So W and C, they have become small. Similarly, we could have print. Oops. Print WCP dot upper. So these are the methods that we can use for converting. Lower, upper, 5 methods are available. Lower, upper, capitalize, swap case and title. Upper, everything will become capital letters. Okay. Then I'll show you what happens in the capitalize dot capitalize. What it's going to do is, oops, capitalize L. Again, my mistake, CAP, capitalize. Okay, so what's going to do is it's going to capitalize only the first letter. Okay, only the first letter. Here the first letter is already capitalized. Okay, let me just make this small, then it will become clear. You can see here, first letter is small. It has turned only the first letter into capital. And basically capitalize WCP dot capitalize, it is going to convert that string into a form that you use in a sentence. In a sentence, only the first letter is capitalized, right? So that's why. So if you want to convert this sentence into what looks like this, so something like this. Suppose you have something like this. Okay, W. Suppose one letter is this one. This is another K, S, like this. Some weird form like this. M, P, U, O, and so on. Okay. Run this, some of these letters are capital, some are small, right? It is going to put everything in one uniform format. Okay, only the first letter is capitalized. Then next is swap case. Swap case, what it does is wherever it is capital, it makes it small. Wherever it's small, it makes it capital. Swap case. Okay, you can see here all the capitals have become small and all the small letters have become capitalized. And lastly, we have title. Title is, let's say, let's say you're trying to write a article. In the article, generally you see the title. The first letter of every word is capitalized. So that title method, it does that. The first the letter of every word is capitalized. Everything else is small. So you can actually do these kind of conversions very easily using strings. Then we have something called as escape sequences. So escape sequences is a combination of two characters. It follows from whatever is there in C, C++. So it means some special things. So let's say I create a variable called as WCP2. Okay. So again, workshop on computational physics. Okay. So now let's say I put an escape sequence /n. Okay. I put a /n here. Then I put a /t here, /t, and run this. Okay, print WCP2. You can see here /n. Wherever there is a /n, okay, wherever there is a /n before on, it went to the next line. Okay, next, wherever there is a /t, it gave one tab space. You see, there's a big one tab space. Okay, wherever there is a /t. Then likewise, there are other some escape sequences also. So suppose I want to put, I want to put this in single quotes, computational. I want to put inside single quotes. Okay. I put inside single quotes, I can do that. Let's say in computational, if I want to put double quotes, let's say double quotes, this is going to give me a problem because double quotes is already there double quotes. So if I do this, it's going to give me an error. But still, let's say I want double quotations here. I could just put / double quote here and / double quote here. This is going to give me the double quotes that I require. Okay, this is because there is a single double quote here, okay, on both sides. So these are basically your escape sequences. Escape sequences are mainly used for putting some special interpretation, some characters special, because you cannot not type next line, going to next line, you cannot type it on from your keyboard. You can't do that. Next we have raw strings. Okay, raw strings, let me show you and give a demonstration that then you'll understand this. So let's say we have a string 1. Okay, so suppose you have a file. Okay, you have a file in your C drive. In your C drive under documents, let's say you have a file. So if I say I want to store the location of that file. So let's say it is in C drive, and under C drive, let's say it is in documents. Okay, and let's say inside documents, let's say there is a new folder. Inside new folder, let's say there is a file called as temperature. Let's say you're storing temperature data. Okay, so I have this is the string, this is the location. So I have in my C drive, there is a folder in the documents folder. Okay, I think this is called my documents or something. Okay, C drive, in the document folder, there is a folder called as new. Inside new, there is a file called as temperature.dat. Okay, so now let me try to print this out. So print S1. Okay, what has happened here? You can take a guess. See, it just reads it. Then it sees, okay, /d, nothing, no problem. It will just print it as it is. It keeps moving ahead. Then it finds /n. What is /n? /n is new line. So it understands this as if you are trying to go to the next line. So it takes you to the next line. Okay, so this new is actually a part of your string, but it is considering this as a next line. So EW, it comes to the next line. Then there is a /t, sorry, backslash, not forward slash, it's /t. So backslash has got a special meaning. It means one tab space. So it gave one tab space, and then it showed the rest of the thing, one tab space, and then whatever is rest, it has printed out here. Okay, that's because of these characters. These are interpreted as escape sequences. So how do we solve this problem? The way to solve this problem is by using what are known as raw strings. So I'll create one more variable. That variable, let me call it as S2. So raw strings, how do you do it? Just in front of the string, just put an R here. That's all. That will tell you that this is a raw string. So Python knows that even though it is seeing a /n, but it will not consider this as a new line. Okay, because it's a raw string. So whenever you are trying to store, let's say the location of files, or let's say you're trying to store the URL, the links of this one, because in links also you could have have, backslash and so on. So these kind of cases always use a raw string. So now if I print this out, it is going to print correctly. See, now it is printed the location whatever I want, it is printing the location as it is. So this is how you can manipulate strings. Now it's 12:42. So Samrat, are you there?
Yes.
So
Yes.
shall we take a break now?
Yes, we can.
What will be a good time? I think 1:20. Let's meet at 1:20.
Yes, should be okay.
1:20 is good. Okay, so let's meet at 1:20 then. Then we'll look at lists. Okay. We'll be meeting on the other link which is mentioned in the for the afternoon session. What is mentioned, that link will be using.